Hey fellow nerds, today we'll learn some applications of op-amps. We'll start with a summing amplifier circuit or a summer. Then we have a differential amplifier circuit, subtractor, followed by an adder-subtractor. Finally, we have instrumentation amplifier and voltage follower, which is also called unity gain buffer. Let us start with a summing amplifier. In case 1, we'll make an inverting summing amplifier. We'll use an ideal op-amp, so gain will be infinite and input impedance will be infinite. First, let us take a normal inverting amplifier. I'm calling the feedback resistor RF, and the resistor through which we are giving the input V in 1 is called R1. This is an inverting amplifier, so V in 1 is going to come out at the output as negative RF divided by R1 multiplied by V in 1. Now, a summing amplifier should be taking the sum of different inputs. So let us give two more inputs along with V in 1, V in 2 and V in 3. Now what happens? V in 1 will come out at the output as negative RF divided by R1 multiplied by V in 1. V in 2 will come out at the output as negative RF divided by R2 multiplied by V in 2. Similarly, V in 3 will come out as negative RF divided by R3 multiplied by V in 3. So the final output will be this. We can take the negative out and write the output like this. You can see the output is actually the weighted sum of the inputs. Now, what if R1, R2 and R3 are all equal to the feedback resistor RF? In that case, this will become 1, this will become 1 and this will become 1. Output will be negative of V1 plus V2 plus V3. Now this is an inverting summer. In the next case, let us make a non-inverting summer. We'll still use an ideal op-amp, so gain will be infinite and input impedance will be infinite. We'll start by taking a normal non-inverting amplifier. I'm calling the feedback resistor RF, and this resistor over here is R. Vin is given as an input through a resistor R1. We want multiple signals to be added, so let us add two more inputs, V in 2 and V in 3. Previously, when we discussed non-inverting amplifier, we did not have an input resistance over here. Because in that case, we only had one input, and we know ideally no current passes through the input terminal. That means no current will flow through this resistor, there will be no potential drop, so it would be pointless. But now we have multiple inputs, and current can pass through all these paths. Now let us call this point X, so the potential over here will be Vx. Like we said, input bias current is 0. No current will flow into the terminal. So current flowing through R1 plus current flowing through R2 plus current flowing through R3 should be equal to 0. Current through R1 will be V in 1 minus Vx divided by R1. Current through R2 will be V in 2 minus Vx divided by R2. Current through R3 will be V in 3 minus Vx divided by R3. The sum should be equal to 0. Let's take all the Vx terms together. Then the equation becomes like this. That gives us an expression for Vx like this. But since we have an ideal op-amp, if the potential here is Vx, potential here is also Vx. That means potential over here is Vx. But what is the potential over here? We have a voltage divider that divides V out. Here V out is being divided between RF and R. Out of that, whatever is dropped across R is the potential we get over here. That means Vx is nothing but V out divided by RF plus R multiplied by R. That means V out is Vx multiplied by RF plus R divided by R. Or Vx multiplied by 1 plus Rf by R. But Vx is what we have over here. Using this expression over here, we get our final expression for the output. And it is 1 plus Rf by R multiplied by V1 by R1 plus V2 by R2 plus V3 by R3, the whole divided by 1 by R1 plus 1 by R2 plus 1 by R3. Now, assume R1, R2, R3 and R are all equal to half of the feedback resistor RF. Now what happens to this equation? RF by R will become 2. So here we get 1 plus 2. V1 by R1 plus V2 by R2 plus V3 by R3 can be written as V1 plus V2 plus V3 multiplied by 1 by R. 1 by R1 plus 1 by R2 plus 1 by R3 can be written as 3 1 by R or 3 by R. Here R and R gets cancelled. 3 and 3 gets cancelled. And the output is simply V1 plus V2 plus V3. What we have is a non-inverting summer. Let us now move on to differential amplifier. A differential amplifier amplifies differential input, or a differential amplifier amplifies the difference between the inputs. Let us start by taking an ideal op-amp so that the gain will be infinite and input impedance will also be infinite. Let's give a negative feedback through this resistor. We need the differential input to be amplified, so we'll give an input at the negative terminal and an input at the positive terminal. V in 1 is given through an input resistor R1. V in 2 is given through an input resistor R3. Now, we know input bias current is 0. So no current is going to flow through R3, which means there will be no potential drop across R3. Which means at this point, the potential V2 will directly come. Potential at this point is constantly going to be at V2. So we will add another resistor R4 over here, so there is a path for the current to flow. Let's say the potential over here is Vx, then potential over here will also be Vx, virtual ground concept. Input bias current is 0. No current will flow in this direction. That means all the current flowing through R3 will flow through R4. Current flowing through R3 is V in 2 minus Vx divided by R3. Current flowing through R4 is Vx minus 0 divided by R4. These two currents should be equal. That gives us this. From this equation, we can write an expression for Vx. Vx is V2 divided by 1 plus R3 by R4. We can do the same thing at the other input also. No current will flow in this direction. That means all the current flowing through R1 will flow through R2. Current flowing through R1 is V in 1 minus Vx divided by R1. Current flowing through R2 is Vx minus V out divided by R2. These two should be equal. Let's bring R2 to this side of the equation. Then we can write V1 R2 by R1 minus Vx R2 by R1 is equal to Vx minus V out. Let's take Vx to the other side of the equation. That gives us this. V1 R2 by R1 minus Vx times 1 plus R2 by R1 is equal to negative of V out. We need an expression for V out. V out is negative of whatever we have in the left hand side. Let us now take negative of R2 by R1 as common from both terms. If you take negative R2 by R1 from this term, V1 will be left. Now we have to take negative R2 by R1 from this whole term. Since we are taking negative out, the plus will become minus. Let's keep this term as it is and take R2 by R1 from this. If I take R2 by R1 from 1, I get R1 by R2. If I take R2 by R1 from R2 by R1, I get 1. This is the final equation we have for the output. Now, assume R1 by R2 is equal to R3 by R4. That means this term is equal to this term. That means this term is equal to this term. V2 is being divided by something and then multiplied by the exact same thing. So these two will get cancelled. And the equation becomes negative of R2 by R1 multiplied by V1 minus V2. Or we can write the output as R2 by R1 multiplied by V2 minus V1. Clearly the circuit is amplifying the differential input. Gain is R2 by R1. Let us now take a special case of this. We have this equation for the output. What if R1, R2, R3 and R4 are all equal? In that case, this will be 1, this will be 1 and this will also be 1. This will be 2, this will be 2, so these two will get cancelled. And V out will simply be V2 minus V1. Our circuit becomes a simple subtractor. Let us now build an adder-subtractor, a circuit that adds some signals and subtracts some others. We'll start with the differential amplifier. Here the output will be V2 minus V1. What we're going to do is add multiple signals over here and multiple signals over here. like this. Now V3 and V4 will come out as positive. V1 and V2 will come out as negative at the output. The output will be V3 plus V4 minus V1 minus V2. Technically, the circuit is adding some signals and subtracting some others. What we have is an adder-subtractor. Now, we'll take two circuits that we already learned, interconnect them and build a better circuit. For that, first we need two non-inverting amplifiers. You can see these are the exact same circuits. The second one is just an inverted version of the first one. Here positive terminal is here, negative is here. Here positive is here and negative is here. Other than that, they are the same. I am giving the input V1 over here and V2 over here. Here the input is V2. We'll call the output V2 dash. Here the input is V1. We'll call the output V1 dash. Now before we move on, I want to draw the circuits in a different way. I'll draw the first one like this and the second one like this. Now we'll take a differential amplifier. I'm gonna give V1 dash as an input over here and V2 dash as an input over here. I'm going to do one more thing. We have a resistor here and a resistor here. For each of them, one end is grounded. That means if we connect them as a single circuit, these two resistors are actually connected like this. In that case, we can replace the two resistors by a single resistor that connects the two non-inverting amplifiers like this. If we do that, the circuit will look like this. What we just built is called an instrumentation amplifier. The first stage is two non-inverting amplifiers. The second stage is a differential amplifier. We will discuss why it is called an instrumentation amplifier and why it is important. But before that, let us find the gain of this circuit. Take the differential amplifier stage. The two inputs are V2 dash and V1 dash. Then we can write the output like this. Here, if R3 by R4 and R1 by R2 are equal, then the output becomes R2 by R1 multiplied by V1 dash minus V2 dash. We have already seen this. Now, assume there is some current flowing through R dash like this. This cannot flow in this direction because input bias current is 0. So all of this current will have to flow through R. Again, this cannot flow in this direction because input bias current is 0. That means all of the current will flow through R and then flow through the other R dash. Let's call the current I. Again, R has a potential V1 over here and V2 over here. So the current I will be V1 minus V2 divided by R. Like we said, no current flows into the Opamp. So currents through R dash and R dash are also I. Now, can we write an expression for V2 dash? We have V2 over here. Out of that, IR dash will be dropped across the resistor. The rest will be equal to V2 dash. So V2 dash is V2 minus IR dash. Let's do the same thing for the other R dash also. We have V1 dash here, V1 here. Potential drop across R dash is IR dash. There is one difference. Here the current is flowing in the opposite direction compared to this one. So using Kirchhoff's voltage law, we can write V1 dash is V plus IR dash. But I is this much. That gives us these two expressions for V1 dash and V2 dash. Let's use these two equations for V2 dash and V1 dash in the expression for the final output, which is R2 by R1 multiplied by V1 dash minus V2 dash. If we do that, this is what we get. These two are the same, so they can be added. We get 2 times V1 minus V2 by R dash plus V1 minus V2. Let's take V1 minus V2 as common. That gives us R2 by R1 multiplied by 1 plus 2R dash by R multiplied by V1 minus V2. Here, what is V1 minus V2? It is our differential input. So the instrumentation amplifier is multiplying V1 minus V2 with this much. Then what is this? This is the gain of the amplifier. We can call it the differential gain because this is the gain with which it is amplifying the differential input. One more interesting thing is we have this R over here. It can actually work as a control for the gain. Gain can be varied by using a variable resistance as R. Obviously, the circuit has a very high gain. Why? Because V2 is being amplified by a non-inverting amplifier at first. V1 is also being amplified by a non-inverting amplifier. Later, they are again being amplified by a third op-amp. So, instrumentation amplifier has a high gain. Let us now talk about its common mode rejection ratio, CMRR. To check that, we have to give a common mode input when inputs are both equal. V1 is equal to V2. If V1 and V2 are equal, then the potential here is equal to the potential here. Potential across R is 0, which means no current will flow through it. I becomes 0. If I is 0, then no current is flowing through R dash, which means there is no potential drop across R dash, which means this potential will be equal to this potential. V2 is equal to V2 dash. Similarly, no current is flowing through this R dash. That means it has zero potential drop across it. And that means V1 is equal to V1 dash. So the input of the differential amplifier stage V1 dash and V2 dash will simply be V1 and V2. In that case, the output will become R2 by R1 multiplied by V1 minus V2 instead of V2 dash minus V1 dash. But V2 and V1 are equal. That means output is 0. What does this mean? The circuit is efficiently rejecting common mode input. For a common mode input, its gain is 0. It is multiplying the common mode input with 0. So the instrumentation amplifier has a very low common mode gain and a very high differential mode gain. What does that mean? It has very high CMRR. Because CMRR is the ratio of differential mode gain to the common mode gain. Instrumentation amplifiers are used to sense physical quantities like temperature. How? Sensors usually measure physical quantities like temperature, pressure, force, etc. and convert them into electrical signals. And these signals are usually very small in amplitude. What an instrumentation amplifier does is it takes the small signal, amplify it accurately and reject any noise picked up along the way. Instrumentation amplifier has a very high gain, so it can accurately amplify small signals from sensors. It will also reject the common mode noises because it has a high CMRR. In simple words, this is how it works. The first two op-amps A1 and A2 give high input impedance and initial gain. The third op-amp then subtracts the signals and remove all the common mode signals. Basically, an instrumentation amplifier has high gain, high CMRR and high input impedance. Let's see the last circuit for today. The voltage follower, which is also called unity gain buffer. This is what the circuit looks like. It's very simple. The output is directly fed into the negative input. Let's say the potential here is Vx, then potential here is also Vx. But Vx is the same as Vout. Vx is also the same as Vin, which means Vin, Vout, Vx are all the same potential. And that means the gain Vout by Vin is 1. The closed loop gain of this circuit is just 1. My question is, if the gain is 1, then how is it useful? It is an amplifier that doesn't amplify. Well, to understand that, let us list out the properties of this circuit first. It has a gain that is equal to 1, but along with that, it has a high input impedance and a low output impedance, just like any op-amp circuit. Let us see how this can be useful. Consider we have a high impedance source connected to a low impedance amplifier. We can model it like this. Input impedance of the amplifier is very low. Output impedance of the source is very high. Essentially, what is happening here is a voltage division. Input is being divided between Rs and Rin. Rs is very high. Most of the input will drop across Rs itself. Only a little bit of it is going to go to the amplifier. Now, this is not desirable. So what we do is this. We know a voltage follower has high input and low output impedance. We'll take it and connect it as a buffer between the source and amplifier, like this. Does it amplify the input? No. Whatever is the input we get here is exactly what we get over here, and it is exactly what is given to the amplifier. But since the voltage follower has a high impedance, we can make sure that most of the input is being dropped over here and not on the RS itself. Technically, we can say that the voltage follower used as a buffer effectively increases the input impedance of the amplifier. So that's all about it for today. See you in the next video.